Hi guys, today I'm going to talk about the mass conservation in moving fluid and how to apply Newton's second law, that is called momentum transfer in controlled volume and heat transport, which is continuous. I'm talking, so let's see. So I was talking about the mass conservation. So first we'll take the example, not example. We'll see. Uh, Suppose fluid is moving. Fluid is moving through this area, entering here and leaving here. So we are going to take, we are locating some control volume, we are taking some volume, and that volume uh, we cannot take below line of the critical volume. If we take this volume, control volumes 1 micron, um, 1 mic 1 curon. So what will happen, this density will fluctuate because of density is equal to mass per unit volume. So, and there is a two approach to track it. One is particle approach and one is second is continuum approach. So we are going to talk about the continuum approach. So we are taking one volume here. That volume should more than the critical volume. Suppose we decided one control volume in a moving fluid. Suppose this is the x direction and this is y direction and this is z direction, x y, and this distance is dx, this is dy, and this is dz. Suppose fluid is entering in the x direction and leaving in the same direction. Suppose, so what will happen, this suppose 5 kg mass of fluid is entering and here we are getting 2 kg. So 3 kg mass is accumulating inside the control volume. So based on that, so what will happen, if you find out accumulation of rate of accumulation is equal to out minus in. So what we'll do, so first we'll see that if we'll talk about the mass flow rate, so mass per second, if we'll talk, so what we'll write, mass is equal to rho into v divided by s. Per time per second we can write like this. So volume, what we can write, rho into L into A into area into height L divided by S. So this L by S means time, L by T, what will happen, this will become velocity. So this rho A V we can write. So this volume is, this mass is entering through this corresponding area. So suppose the fluid is entering with the u velocity in the x direction and fluid is entering with the v velocity in the y direction and w velocity in a z direction. So what we'll do here, so if we'll take it in x direction, so the mass entering in the x direction, so what we'll write, rho u velocity in the x direction and this corresponding area dy into dz. So this is the mass entering in the x direction and leaving in. So now we'll go for the mass leaving. So from the Taylor series expansion, either the in general form we can write it if fluid is here and this, after this dx distance, what would be the mass? So rho u in the x direction, rho u dy dz plus dy dx, rho u dy dz into dx. This mass is living in the x direction. In the x direction. So if we'll talk about the accumulation in the x direction, so what we'll do, entering mass rho u dy dz minus rho u dy dz minus d upon dx rho u dy dz into dx. So this will be cancelled, and accumulation in the x direction will get it minus d upon dx rho u dy dz into dx. We can write it dx rho u dy dx dy dz. So if we'll talk about the y direction, so in the same way you can write it. If the fluid is entering in the y direction and leaving in the same direction, so what we'll do, we can write it d dy rho b dx dy dz. For z direction, dz rho w dx dy dz. So if we'll talk about if we'll take it as a whole, then we'll add it the total volume. So we can write it like minus d upon dx rho u plus d upon dy rho b plus d upon dz rho w dx dy dz. And if we'll talk about this accumulation, this control volume, so this mass is not going to change. This mass is not going to change if we take inside the control volume. So what will be the mass? This mass will be rho into b. So this rho into dx into dy into dz, that is total volume of the. And if we take rate of accumulation of the mass, d rho by dt dx dy dz. So this is the accumulation, and this is the equation second, and this is the equation first. If we compare this equation and equate this, we'll get it the value like d rho by dt plus dy dx rho u. This will be cancelled, and this rho u plus dy rho b plus dy dz rho w. This we can write it d rho by dt plus delta dot b divergence. This is equal to 0, and this. So in that way we are going to compute that velocity profile and whatever the need. So if we'll talk about the here force. The second video I will come with the Newton's second law, how to do it. That will consider that all forces acting inside the control volume, and we'll do that, balance that forces, that is called momentum transfer, and we'll go for the heat transport, that is called the first law of thermodynamics. And in that way we are going to compute. So this is my a small video regarding this, whatever I wanted to talk. Then after I can go for the approach whatever I was talking previous. So okay, bye.